We are Hephaestus and will be presenting our project, the Stationary Throttle Intermediate Housing Leak and Functional Tester. My name is Nicholas Ward and I'm the team leader. Camila Miglio is the lead design engineer, Katia Martinez is the project administrator, and Adam Janhowie is the design engineer. Our sponsor is eControls and our mentor is Victor Martinez, a manufacturing test engineer. eControls designs and manufactures electromechanical engine control systems. It has an on-site R&D department and production lines. One of the production lines assembles the stationary throttle. Stationary throttles are used to adjust the airflow into an engine to control the power output, and it does so by restricting inlet gases. Currently, the stationary throttle is fully assembled before it is leak tested, so a faulty unit is only detected at the end of the process. The end-of-line tester does not detect the faulty component responsible for the leak failure. This results in long troubleshooting times and a high scrap cost of $6,000 a year. The part that causes the most failures is the intermediate housing subassembly. It contains two check valves that protect the circuit board from overpressurization. The valves are manually inserted using an arbor press. During installation, the check valves can undergo deformation, which can cause leaks within the valve. The purpose of the project is to design a leak tester that ensures the intermediate housing subassembly meets operational requirements. More specifically, it must ensure that the valves were properly installed, that they crack at the pressure for which they are rated, and that they have an allowable leak rate below the cracking pressure. There are a few key features that the design must include, such as a nesting fixture with alignment features to locate the part and help seal around the pressure ports, and a clamping mechanism to provide the force needed to seal the intermediate housing. Meanwhile, the design needs to maintain production efficiency with quick load and unload times. Lastly, the tester must include proper machine guarding and a two-hand no tie-down system to protect the operators from injury. Now we'll take a look at the design. The leak tester consists of an actuator, frame, holding fixture, and two-hand no tie-down subassemblies, and it is enveloped by a safety enclosure. The most critical subassembly of the tester is the holding fixture, as it is essential to secure, seal, and pressurize the intermediate housing. Rough locating pins and alignment pins ensure that the part is properly positioned within the holding fixture. The pressure ports on the unit are sealed by tapered bullet seals. A spring-loaded mechanism was implemented to achieve the desired seal compression to seal around the pressure ports. A spring pin is used to prevent rotation of the bullet seal holders. The bullet seal holders are the most important components of the holding fixture, because they must always align with the pressurization ports and slide without binding in the holding base. For these reasons, they have the tightest tolerances and surface roughness requirements. In order to validate the calculated clamping force required to seal the intermediate housing, a clamping force analysis was performed. A force of 273 pounds was estimated to compress the high aspect ratio seal on the unit. This estimation was validated using a load cell. 303 pounds of force achieved a gap of less than half of a thousandth of an inch between the intermediate housing and the clamping plate. The actuator subassembly provides a force of 600 pounds to seal the unit. In addition, it is equipped with a coupler which is capable of tilting 2 degrees to adjust for part variations due to casting. The frame subassembly is used to fix the holding fixture to the workbench, to support the actuator above the holding fixture, and to locate the two-hand no tie-down system. Finally, the safety enclosure envelops the tester to prevent potential injuries to operators caused by pinch points created during operation of the tester. Now we are going to discuss the testing phase. In this table, we can see the status of the 11 tests performed. As shown, all tests were completed. Here we can see the test matrix showing the testing procedures that fulfill each performance specification requirement. As shown in the rightmost column, all requirements are compliant. The leak test was the most important test performed. The leak test setup is displayed here. In figure 21, we can see the three-way valves and regulator used to operate the actuator in order to clamp and seal the intermediate housing. In figure 22, we can see the leak testing apparatus and program used to determine the leak decay. This is a screen recording of the leak test program. There are 4 main phases. They are the prefill, fill, stabilization, and testing phases. As a safety measure, a two-hand no tie-down control was implemented. This system requires the operator to push and hold both buttons until the actuator is fully extended for the test to start. The purpose for this is to protect the operator from inserting their hands in pinch points during the operation of the tester. If one of the buttons is released prematurely, as seen in figure 25, the cylinder retracts. Not only is it important for the tester to function as intended, but it has to be ergonomically safe for the operator. E-Controls uses an ergonomic reference stick to define the permissible zones of reach for an operator. The green and yellow zones are acceptable zones, while the red zone is unacceptable. Since the tester only requires that the operator reach within the green and yellow zones, the ergonomic test passed. Now we are going to discuss project management. Here you can see the project Gantt chart. We began the project in the design phase. Next, the parts were procured and the tester was fabricated. After being assembled, the design was tested to ensure that it met the criteria stated in the performance specifications. Finally, the project was delivered to E-Controls on schedule. The earned value management graph shown here displays the cost of labor for the project. The actual cost of the project was less than the budgeted cost of work scheduled, and the cost variance was $3,970. To sum up, fabrication and testing of the project was completed. All validation tests passed. The intermediate housing leak tester is working as intended and has an operation time of approximately 2 minutes. The project was delivered to E-Controls on schedule and on budget. The tester will generate a return on investment of $36,000 over the next 6 years. The main lessons learned from the project were to be consistent between metric and standard systems, unify hardware sizes, automate calculations using spreadsheets, and review critical design components with experienced engineers. The main lesson learned was that designing is an iterative process. After the initial design, there's much redesigning that must be performed to reach the final product. Thank you.